The development of electronic digital computers began with early man, who used his digits or fingers to keep track of the things around him. One weapon, 2 animals, and 3 wives. Through the ages, a number of digital devices were developed. The abacus, for instance, is still widely used today. Later, more sophisticated models were built by mathematicians to meet the increasing needs of an advancing civilization. Today, business, science, industry, and national security have an ever-growing demand for fast, accurate computation, data processing, and record keeping. The notion that an electronic digital computer is a brain is a common misconception, largely due to a lack of knowledge about the functions and abilities of a computer. But what actually is a computer? What does it do? How does it work? To begin with, a computer is built with electronic components, similar to parts used in a radio or television set. The basic building blocks of today's computers are called semiconductors, such as diodes, transistors, and integrated circuits. Semiconductors are thin wafers of pure polycrystal silicone, sliced into individual chips, less than a centimeter square. So small, you can see 16 of them on this printed circuit, each of them capable of doing the work of 1,000 old-style vacuum tubes. Tiny semiconductors attached to printed circuit boards are inserted into cabinets which interconnect them, and the result is the computer, which can calculate, store information, and communicate. Computers fall into 2 categories, analog and digital. The analog computer is essentially a measuring device, such as a speedometer, which translates and computes drive shaft revolutions into a miles per hour figure. The digital computer is a machine that counts digits and performs normal arithmetic functions. For example, an adding machine is a digital computing device. A digital computer has its own language, through which man communicates with the machine. This means that communication is provided by using the binary number system, which consists of 2 characters, 0 and 1. Combinations of these characters can represent numbers, symbols, words, or letters. These binary 1s and 0s are used to represent the presence or absence of a signal or a switch in an on and off position. In order to use these bistable or on and off conditions, most components in a digital computer are electronic switches. In binary form, the number 5 is represented by 1, 0, 1. In a given position, each binary 1 represents the presence of a definite value, and each binary 0, the absence of a value. In this case, we are concerned with the presence of given values corresponding to the position of the binary 1s. When these given values are added, they total 5. Like the decimal system, binary numbers can be added, multiplied, divided, and subtracted. We have seen how a computer must be provided with the information it requires. However, this information must be introduced to the inner workings of the computer. To do this, many different types of input equipment may be used. In common use today are punched cards, punched paper tape, magnetic tape, and magnetic discs. This is a typical punched card. The position of the holes represents the information written at the top. This punched paper tape frame, the frame is a unit of information, presents information in a similar manner. The combination of holes stands for 3,456. Magnetic tape and discs represent the same type of information. Instead of punched holes, magnetized spots are used to represent data. With punched paper, tape, or cards, the detection of information is achieved through the sensing of each hole by photoelectric cells. The presence of a hole is then converted into a specific signal. The information on tape and discs is detected with magnetic read heads, which also translate the presence of a magnetized spot into specific signals. Some information fed into a computer is immediately involved in computation. Other information is introduced for use at a later time. This information must be retained or remembered until it is called for. In order to do this, the computer uses a memory. Two examples of such memory are the magnetic drum and magnetic cores. The magnetic drum uses a similar recording method as magnetic tape. The information stored on a drum is divided into hundreds of tracks. Each track is made up of thousands of cells, and each cell represents a binary 1 or 0. The magnetic core memory is made up of tiny donut-shaped magnets, which can be switched from one polarity to the other, thereby indicating the absence or the presence of a 1. Magnetic cores are even faster than a magnetic drum. Stored information is available in microseconds, or millionths of a second. The various sections of the computer and their internal operations are controlled by a series of electrical timing pulses, called the clock. This is much like the beat or rhythm of a musical composition. Every time an upbeat or downbeat occurs, certain notes are played or not played. The same holds true in a computer. Every time a clock pulse occurs, certain operations are performed by the various electronic circuits. These pulses enable the computer to direct and time its operations. A digital computer is not a brain, although the nature of its functions parallel those performed by a human being. Let's take the average taxpayer. Hardworking, diligent, honest. Our friend must perform certain tasks in order to complete his tax form. We can analyze these functions and say they fall into 5 general categories: input, memory, arithmetic, output, and control. Control, in this case, is the brain of our friend. The computer would handle this particular problem in much the same fashion as the taxpayer. All the deductions, income, and taxes would be channeled into the memory section of the computer to be called out when they are required for a calculation. The memory would also hold the rules and regulations governing the preparation of a tax return. The arithmetic section would perform the calculations needed to solve the problem. Subtract the deductions from the total income, figure percentages. The results of these calculations could be stored in the memory or sent to the output section. The entire operation would be governed by the control section, which in effect is comparable to our friend's figure-heavy head, except that this control is governed by the rules and regulations stored in the memory. Let's stop for a moment and see how the computer performs some of these tasks electronically. Digital computers, which process binary information, use a series of basic logic blocks. These logic blocks, when translated into electronic hardware, make simple decisions, such as yes or no. Is it a 1 or a 0? One of these logic blocks is the answer which can provide one yes decision if both inputs are ones. The key to its function lies in the word itself. If input A and input B are 1, the output is 1. Any other combination of inputs will produce a 0 answer. Another logic block is the OR circuit, which provides 3 yes decisions. If input A or B are 1s, the output is 1. The last combination of inputs will produce a 0 answer. The third logic block is the inverter. This circuit will change a 1 to a 0 or a 0 to a 1. These basic logic blocks in a digital computer are combined in many ways to achieve different results. Let's see how some of these logic blocks can add 1 to 1. We would use 2 AND circuits, an OR circuit, and an inverter. Now let's add a 1 to another 1. One will go into input A and the other into input B. Input B is channeled to the OR circuit and the AND circuit. The same holds true for input A. Since input A and B are both 1, the output of the AND circuit will be 1. However, the inverter will take this signal and change it to a 0. The carry or a 1 signal bypasses the inverter. The output of the OR circuit is 1, since the inputs contain a 1. The last step is the output of the AND circuit, which is 0, since both inputs are not 1s. The carry held a 1. Therefore, the final answer is 1, 0, which is the binary representation for 2. Now let's add a few more logic blocks and build a 2-bit adder. An adder which can add binary numbers not to exceed 2 digits in length. Let's add 1 and 2. In binary form, 1 is represented as 1, and 2 is 1, 0. The 1 is channeled into input A, and the 1, 0 into input B. When a computer receives the command to add, the addition is made. The answer is 1, 1, which in binary represents 3. There are a number of other logic blocks which are derived from AND, OR, and inverter circuits. Their functions retain strong similarities to the very basic logic blocks. Combinations of all these logic blocks enable the computer to perform addition, multiplication, division, and subtraction at the rate of several million per second. The results of these computations can be monitored by the computer operator. The control console provides a display of the contents of data in most parts of the computer. How does a computer know what to do and when to do it? With man, the execution of a particular problem is comparatively easy, since conditioning, education, and intelligence make it an almost automatic process. However, the computer doesn't possess any of these attributes. Therefore, man must generate a series of commands and instructions to execute the various steps of a mathematical problem. It is important to note that the computer is useless unless man does prepare a series of commands. In effect, telling the computer exactly what to do and when to do it. This function of man is called programming. Now let's look at our friend again and approach his particular problem from a programmer's point of view. First, we must analyze the problem and prepare a flowchart. Given a start signal, the programmer will set down all the facets of the problem in proper sequence. Wages, added to gambling or other income, including capital gains. This will provide the gross income. In order to arrive at the net income, contributions, medical expenses, and other deductions are subtracted from the gross income. This net must be remembered. Therefore, it is stored. Now, the amount of tax due can be computed. Is the net more than $2,000? If no, multiply by 5%. Print out the answer and stop. Is it more than $4,000? More than $6,000? More than $8,000? More than $10,000? If yes, somebody goofed and the problem is begun anew. Although this particular example is oversimplified, it does point out the extreme care taken in planning various steps to arrive at a correct solution. So far, we have seen how a computer performs essentially the same functions as man. The main difference lies in the computer's greater speed and its capacity for a huge amount of data. We have caught a glimpse of its so-called intelligence, which is really nothing more than an ability to distinguish a binary 0 from a 1, or the presence or absence of a signal. We have also formed an idea of how a computer is directed to execute certain functions it has as prescribed by man, the programmer. Once again, we will call upon our friend, the taxpayer, to firm up our knowledge of the digital computer's operations. We have mentioned instructions the computer can understand. What exactly are their distinguishing features? Each instruction consists of several commands, much like a set of travel orders or itinerary. Each different instruction calls for several different steps to take place. These steps are the commands. An instruction is much like the situation that exists in the electric clock system, which is used in schools. When a predetermined time has been reached, it will set off a series of events. For instance, the clock will set off a bell or buzzer system in each classroom, announcing lunchtime. This time signal, in effect, has a general reaction that follows a specific pattern of events until the next buzzer sound comes along, indicating the beginning of a series of sequential events. And so it is with the instruction in a computer. For example, this is a transfer instruction, which means that information from one or more sections of the computer is to be transferred to another location. Specifically, it can stand for the following. Take information stored in memory and transfer it to arithmetic. Also, take information from input and transfer it to arithmetic. The next instruction will specify the disposition of the results of this computation, whether it is to be stored or sent to the output section. Of course, there are many more instructions, each standardized to perform a particular phase of a problem. And the instructions may vary with each computer. But basically, the instruction is the kickoff to a series of events the computer performs automatically. We have seen a digital computer as it really exists, a machine using binary numbers representing data. This data is fed to the computer through the use of punched cards, paper tape, magnetic tape, or magnetic discs. The computer stores this data on magnetic cores, magnetic drums, plated wire, magnetic discs, or magnetic tape. The typical digital computer uses very simple logic blocks, which can only distinguish 1 from 0. We have also seen the computer divided into 5 main sections, each section responsible for a series of tasks or operations. We saw how the solution of even a simple problem needed detailed analysis and direction. As we have seen, a digital computer is just a machine. However, it can do a few million arithmetic functions per second and without error. It can do tedious and extremely difficult mathematics in such a short time that the comparison between man and machine becomes almost unbelievable. One man working 8 hours a day, 5 days a week for a whole year, can do what the machine will complete in a matter of hours, or even minutes. Keeping such facts in mind, it becomes easy to understand why business, science, and industry are making such tremendous demands upon computer technology. At Sperry-UNIVAC, this technology has been used to develop a variety of machines. These range from computers for the U.S. Bureau of Census to shipboard computers for naval tactical situations. Man's continuing exploration of the space frontier would be virtually impossible without this efficient tool. Computers are being used to speed up the varied, tedious tasks which are essential to our progress and growth. Computers are providing man with more time for creativity. They are greatly aiding the generation of today in ways undreamed of a few short years ago, as they also shall aid the judgment and intelligence of those yet to be heard from.